Hello everyone. Welcome to the ILTA Physics Online. Today, we're going to study Newton's three laws of motion together. These three laws that Newton established are not just simple formulas, they completely change the way we understand how objects move. We're going to cover three things today: Newton's first law, second law, and third law. The first law is often called the law of inertia, the second law is called the law of acceleration, and the third law is known as the action-reaction pair. All right then, let's go through these three laws of motion one by one. Before we get started, let's quickly review what we learned last time about force. In dynamics, we define force as the cause of motion. To put it more precisely, it's any influence that changes an object's velocity. One important thing to remember is that in dynamics, a force always involves an interaction between two objects. The object applying the force is called the agent, and the object that receives the force and moves is called the object. A force has both magnitude and direction, so it's represented as a vector. And depending on how it's applied, forces can be divided into contact forces when two objects are touching and long-range forces when they act at a distance. As you can see in the picture below, the toy car that the child is sitting in is the object, and the two children pushing from behind are the agents. Since they're pushing to the right, we can represent the forces they apply as arrows, labeled F1 and F2, respectively, both pointing to the right. In last lecture, we also briefly mentioned some of the different types of forces that we'll be studying in detail later. Don't worry if the names sound unfamiliar or if you don't remember the details yet. We'll take our time and go over each type carefully in future lessons. Now let's start with Newton's first law. In simple terms, the first law says that an object at rest stays at rest, and an object in motion stays in motion. Sounds obvious, right? But here's the key condition. This only happens when there's no external force acting on the object. So, in other words, if no external force acts on an object, a stationary object stays still, and a moving object keeps moving at the same speed and in the same direction. Take a look at the examples below. A soccer ball sitting on the grass and a wooden box resting on the floor will both just stay where they are if no external force acts on them. But what happens if you suddenly kick the soccer ball? The ball will fly upward. Even after it leaves your foot, meaning there's no more contact force, it keeps moving through the air. A moving object keeps moving without external force. That's exactly what Newton's first law says. The same goes for the box on the floor. If you push it to the right, even after your hand lets go, it keeps sliding to the right for a while. This might sound like common sense, but let's pause and think carefully about two key points here. We can easily accept that a stationary object will stay still if no force acts on it. But Newton's first law also says that a moving object will keep moving at a constant speed in a straight line if no force acts on it. That actually sounds a bit strange, doesn't it? Because in real life, when you kick a ball, it doesn't keep flying forever. It eventually slows down and falls to the ground. And when you push a box, it slides for a while, but then stops. So, does that mean Newton's first law is wrong? Not at all. The reason the ball eventually falls or the box slows down is because external forces are acting on them. Things like air resistance and friction with the floor. These forces cause changes in their motion, just like we discussed in the last lesson. So, as it says here again, Newton's first law tells us that if no external force acts on an object, it will maintain its current state of motion. There's one more important thing to consider in this law: the concept of unbalanced forces. In the middle diagram, for example, two people are pushing on the same object from opposite directions. Even though both are applying forces, those forces can cancel each other out. If the total or net force adds up to zero, the object won't move at all. So when multiple forces act on the same object, we calculate the net force by adding up all the force vectors. If the net force equals zero, That is, if the external forces are balanced, then Newton's first law applies. The object will stay at rest or keep moving at a constant velocity. All right, let's move on to the next page and think about the first law a little more deeply. Newton's first law is also known by another name, the law of inertia. As we explained earlier, the law of inertia describes the motion of an object when no external force acts on it. That means a stationary object stays at rest and a moving object continues to move at the same speed and in the same direction. Now, let's talk about the word inertia itself. You'll learn more about it later in physics, but simply put, inertia is the tendency of an object to resist any change in its state of motion. In other words, it resists changes in its velocity. In general, the greater the mass of an object, the greater its inertia. Think about this in everyday life. Which is harder, pushing something light or pushing something heavy? Of course, it's harder to push a heavier object. That's exactly what Newton's first law, the law of inertia, is describing. Here's a classic experiment that demonstrates inertia. You place a thin card on top of a cup and then put a coin on top of the card. Now, if you flick the card quickly with your finger, the coin doesn't move forward with the card. Instead, it drops straight down into the cup. That's because the coin was at rest and wanted to stay at rest, maintaining its original state of motion because of the inertia. Now let me quiz you to check your understanding of Newton's first law. If an object is moving to the right at a constant speed, in which direction is the force acting on it? Many students might think, well, it's moving to the right, so the force must also be to the right. But here's the key point. It's moving at a constant speed. According to Newton's first law, if no external force acts on an object, it continues moving at constant velocity. That means, in this case, the net force on the object is zero. This is a concept that confuses a lot of students, so make sure you think about this carefully. All right, now let's move on to Newton's second law. Let's recall what we just learned about the first law. When no external force acts on an object, it maintains its state of motion. For example, as shown in the picture on the left, if a toy car is at rest and no force acts on it, it stays at rest. But what happens if an unbalanced external force acts on it? Let's say a mother pushes the toy car from behind. That means an external force is being applied. Naturally, the toy car begins to move forward. In other words, its velocity changes. And that change in velocity means that acceleration is produced. So, an external force causes an object to accelerate. And that's exactly what Newton's second law says. When an external force is applied, it causes acceleration in the object. Here, two words are really important: force and acceleration. Newton's second law quantitatively describes the relationship between them. Let's think about that relationship intuitively. We'll start with what we already know from experience. First, think about how the magnitude of the force affects the magnitude of acceleration. In the picture on the left, a small child is pushing a toy car with another child sitting in it, but he's struggling. In other words, he's applying a small force. So the car will move slowly with only a small acceleration. Now, look at the picture on the right. This time, the child's mother pushes the same car. Since mother is stronger, she applies a much larger force, and the car moves much faster. That means the acceleration increases. From this, we can conclude that the acceleration of an object increases as the applied force increases. A small force causes a small change in speed, while a large force causes a larger change in speed. That's the first intuitive relationship. Acceleration is positively related to force. Now let's think about the directions of force and motion. If you push an object to the right, it moves to the right. That's obvious, right? If it moved left when you push to the left, that would be magic. So, the direction of the force is the same as the direction of the object's motion. And since the acceleration is the change in velocity, the direction of acceleration is also the same as the direction of the force. That makes perfect sense. Finally, let's think about the relationship between acceleration and mass. If you push a light basketball and a heavy car with the same amount of force, which one speeds up more quickly? Of course, the basketball does. The heavier the object, the smaller the acceleration. So, acceleration is negatively related to mass. That means when you apply the same force, heavier objects have smaller accelerations and lighter objects have larger accelerations. These are all intuitive facts that lead directly to Newton's second law. Now, let's describe Newton's second law more quantitatively. It's called the law of acceleration, and it mathematically describes how force relates to changes in motion. In other words, changes in velocity. We won't go into complex calculus here. Instead, we'll rely on experimental observations. First, we know from experiments that acceleration is directly proportional to the applied force. If you double the force on an object, its acceleration doubles as well. Second, the proportionality constant between force and acceleration depends on the mass of the object. From our earlier discussion, we know that heavier objects experience smaller accelerations under the same force, so acceleration is inversely proportional to mass. Finally, the direction of acceleration is the same as the direction of the applied force. If you push an object to the right, it accelerates to the right. Combining these three facts gives us the famous formula known as Newton's second law. Acceleration is proportional to the applied force and inversely proportional to mass. When you rearrange the relationship for force, you get the equation everyone knows. F equals ma. You've probably heard this equation before. It's as famous as Einstein's equation, E equals mc squared. So today, you've just learned the real physical meaning behind Newton's second law. Here, the force we are talking about means the net force. Because as we discussed before, when more than one force acts on an object, the total or net force is the vector sum of all individual forces. The unit of force is named after the scientist Newton, and we call it a Newton. From the equation, we can see that 1 Newton equals 1 kilogram times 1 meter per second squared. Finally, let's look at Newton's third law. At the beginning of this chapter, we said that a force always involves two objects, the one applying the force, called agent, and the one receiving the force, called object. Newton's third law explains the relationship between force and motion from the distinct perspectives of the agent and the object. It can be stated like this. If one object exerts a force on another object, then the second object exerts an equal but opposite force on the first. Sounds a little complicated, right? Let's look at a picture to make sense of it. Imagine a swimmer pushing against the wall of a pool to start swimming forward. The swimmer's feet push backward on the wall, and at the same time, the wall pushes the swimmer forward with an equal force. It might sound strange that a wall can push a person forward, but that's exactly what happens. Here's another example. Imagine walking forward and accidentally bumping your head on a glass door you didn't notice. You hit the glass with your head, but your head also hurts, right? That's because the glass pushed back on your head with the same amount of force in the opposite direction. That's exactly Newton's third law in action, called the action-reaction pair. In physics notation, if object A exerts a force on object B, we write that as F sub A on B. In this case, A is an agent and B is an object. Then object B exerts an equal and opposite force, F sub B on A, back on A. Since the forces are in opposite directions, we can write this mathematically as F sub on B equals minus F sub B on A. Newton's third law is also known as the action-reaction law. It means that every force exists as part of a pair, an action and a reaction. Let's take a look at an example to make this clear. Imagine hammering a nail into a wall. In the first picture, the hammer hits the nail. That's the action force. The hammer is the agent, the nail is the object, and the force is the red arrow directed to the right. But at the same time, the nail exerts an equal and opposite reaction force on the hammer. Now the nail is the agent, the hammer is the object, and the force is the blue arrow directed to the left. The magnitudes of these two forces are exactly the same. So, if you ever bump your head on a glass door and it hurts, remember that's Newton's third law in action. There's one common misunderstanding I want to clarify. Sometimes people draw both the action and reaction forces on the same diagram, but that's incorrect. For example, in the hammer and nail case, the red arrow shows the force on the nail, while the blue arrow shows the force on the hammer. Since these forces act on different objects, you can't combine them in a single diagram to describe motion. A similar mistake happens when people talk about a horse pulling a cart. They say, if the horse pulls the cart forward, and the cart pulls the horse backward with an equal force, shouldn't they just stay still? That's the same misunderstanding. Those two forces act on different objects, not on the same one. So, Newton's third law tells us that each pair of interacting objects experiences equal and opposite forces, but those forces never cancel out because they act on different bodies. And that concludes our study of Newton's three laws of motion, the foundation of classical dynamics. We've got to remember this. The first law is about how an object moves when no external force is acting on it. The second law mathematically explains the relationship between an object's movement, that is, its acceleration when an external force is applied. Finally, the third law interprets the motion from the separate viewpoints of the agent and the object. In the next session, we'll apply these laws to solve some example problems. That's all for today's lecture, and remember, be careful around glass doors. They can push back. Great work, everyone. See you in the next lecture.